nanoHUB.org.
Online simulation, and more for nanotechnology.
Thank you all for joining us for our webinar today, DFT with SIESTA, Data Visualization in a Sophomore-level CURE with the MIT Computational Nanoscience Toolkit. Our presenter, Dr. David Strubbe, is Associate Professor of Physics and Chair of the Physics PhD program at the University of California, Merced. He has been using and developing in nanoHUB since 2008, and he's also done some webinars with us before. You may have joined us for those. So thank you very much for being here today, Dr. Strubbe.
Okay, thanks a lot. Well, I'm glad to be here to speak to you all this morning for me, and maybe some other times for the rest of you. Got my nanoHUB T-shirt on here for the event. And since we were just talking about where people are, I'll note, so I'm at the University of California, Merced. So this is the newest campus of the UC system. And here's a little map to show you where we are, in case you're not familiar with Merced. So we're kind of right smack in the middle of California, and about 2 hours drive away from the Bay Area. And so I'm excited to tell you about some of the things that I've been doing with nanoHUB to enhance a couple of different courses that I've been teaching. So I want to focus on an activity that I did for our class called Physics 10 here. So this class is referred to as Introductory Physics 3, or also Modern Physics, the same kind of name that that many other campuses have. This is an activity that I did this fall, as well as the one before. So this class is for sophomores, so the second year, for about 20 students, and this is for the undergraduate physics majors. So the Introductory Physics 1 and 2 is taken by basically all science and engineering majors, but this class is where the physics majors now are taking a class that is really focused for them. This class is mostly about quantum mechanics, but in a sort of a gentle introductory way, and they have a later, more intensive course. And it also is designed to introduce in a more intensive way lab exercises, like including lab reports. And so some of the topics that are discussed in the class are the Schrödinger equation, particle-in-a-box model, scattering from step potentials, some atomic and nuclear structure in mostly a kind of phenomenological way, a little bit on the quantum statistical distributions, and discussion about particles versus waves. And so my goal in thinking about this class and nanoHUB was to have an activity that would improve learning of quantum mechanics by showing an application to condensed matter physics, to show an example of how we can use computation in modern physics research, and also to help students feel like physicists as opposed to just physics students, and promote them continuing in the major. And the basic idea for that that I decided to adopt is called a course-based undergraduate research experience, or CURE. I think this name is a little bit of a pun originally, in that it started off in biology and things that related to screening drug candidates, but hence CURE. So the idea is to bring the excitement of research into the classroom, not just to tell students about some research that we're doing, but actually to involve them in the research project itself. So some of the key aspects here are that students should learn and use real research methods. They should have some ability to give input into the project itself. They should generate new data. And most importantly, they should be trying to draw conclusions that are not known beforehand. So this is a big difference from the usual kind of labs that we would do in undergraduate physics, and also all of the other labs that exist for this class, which are can be called cookbook style ones, and that there's a list of things to do, and you should just do exactly those things. And if the lab manual is written correctly, every single step is predictable, and just if what you get differs from that, you're wrong, and if it's the same, then you're right, and that's what the goal is. And these are sometimes referred to also as verification style labs, namely that there's something that we know to be true, like Hooke's law for springs, and the goal is just to get that result. And so it's fine. These things have their place. But the interesting aspect for CURE is it's been shown by a number of studies that doing this can promote learning and motivation and independent thinking, and increase the probability that students want to continue being science majors. By applying their knowledge and getting a taste of research, this increases a sense of belonging, like they feel like they are part of the group and even part of a scientific enterprise, and helps to increase the likelihood that they go on to do some more intensive research project outside of the classroom. And it's been shown that these effects, especially the feeling like a scientist and sense of belonging, is particularly beneficial for minoritized or underrepresented students, which is an issue that we think a lot about at UC Merced, because our undergraduate student body is just over 50% Hispanic. So two nice freely available resources that one can read about CUREs are these two that I have down here, both of which come from the Research Corporation for Science Advancement. So there's some kind of ebooks that talk about both what the studies are on CUREs, as well as some practical tips of how you can actually design one yourself. So as I mentioned, the kind of classic or original version of this is something like you have a large number of drug candidates, and students can all do the same thing involving pipetting into a petri dish or something and see whether the bacteria grow or not. And you try to decide from that which of these molecules might be good at killing bacteria, something like that. So you have something that's sort of parallelized with a simple protocol. And so I thought we could do the same thing in condensed matter physics with materials. And in particular, we can use computation, because compared to trying to do a bunch of experiments for the undergraduates, this is something that is cheap, it's well-defined, it's reproducible, and with not too much effort, we can actually easily get to the frontiers of knowledge. So, I mean, basically, if you just think of any material that people have studied, I mean, if you just change the structure slightly, you put in a different atom, move the atoms around, you are almost certainly looking at something that nobody has calculated before. Okay, it's not always interesting in every case, but you are actually at the frontiers of knowledge by doing that. And the equivalent on the experimental side, I think, is much more difficult to get to. And so I chose as our target to look at 2D materials. So this is a slide that I showed in actually in the class. And probably many of you are familiar with this already. I mean, so 2D materials are just an exciting topic in condensed matter physics today. We've got all of these different materials like graphene, boron nitride, transition metal dichalcogenides, et cetera. And they're actually also easier to visualize and easier to run calculations on in some respects than bulk materials. So that's also a nice thing from the pedagogical point of view. And so what I came up with as a task for the students was to think about quantum well structures in two-dimensional materials. So something that's well established in kind of optoelectronic technology for lasers and other things like that is that you have these structures like of aluminum, gallium arsenide, and gallium arsenide that confine some of the wave functions in a particular region. That's the quantum well. And so that can be used to tune exactly what the energies or frequencies of light are that can interact with this structure. And so this is a nice example of quantum confinement that can be described with a particle-in-a-box model. And that's something that they're studying in this class. And so the idea is here we're going to look for structures in 2D materials that could be described by this same model. We're going to try to assess whether the model shows us what's happening and whether quantum confinement is going on. So what we can do is take pairs of materials with similar structures, like the series of transition metal dichalcogenides, and you can make structures where we have these alternating strips like this, and calculate the wave functions and see whether they look like this simple model or not. In some cases they will, and in some cases they won't. It has to do with basically what these band offsets are between them. And we can try all kind of different possibilities where we don't necessarily know the answer yet, and then try to identify ones where there's something interesting that we could then follow up with more intensive calculations and even recommend to some experimental colleagues. Okay, and so our tool to do that is, of course, nanoHUB, which is why we are here on a nanoHUB webinar here, and specifically the MIT Atomic-Scale Modeling Toolkit. And so just a little bit about all of this. So as you may well know here, nanoHUB is a project that started with in the early 2000s, headquartered at Purdue, and you can find simulations, course resources, webinars like this one, and forums there. And a nice feature is that all of the computation that you're doing is actually happening on their clusters. This is a point that students often find not obvious, but so right, we're going to do some calculations, and those things are all actually running remotely. They're not running in your browser, so you can do this from a phone, from a tablet, anything like that. It doesn't matter how much computation power you have, because they're providing it. Here's the link, which you've seen in the chat as well. And so a little bit about the history of this toolkit. It actually began for a computational nanoscience class at UC Berkeley, which was developed originally by Elif Ertekin, who's now a professor at Urbana-Champaign, and Jeffrey Grossman at MIT. And okay, this is actually left in from another talk here. And so I actually got the name wrong in the title for this webinar, which is a little bit embarrassing. It was known as the Berkeley Computational Nanoscience Toolkit at that time. Then Jeff went to MIT, and it was rebranded as the MIT Atomic-Scale Modeling Toolkit. So I sort of mixed up the two, but it is both atomic scale modeling and the computational nanoscience. So I actually got started as a teaching assistant for that class in developing this model. And since 2016, when I started as a faculty member at UC Merced, I've been the main developer, and also done, also some of the work has been done by my former student, Enrique Guerrero. Key points here are that we have some complicated codes under the hood, but we're trying to make it as simple as possible for students to be able to engage only with the aspects that we're trying to have them learn about, and not have to deal with all kind of other complicated things that are not necessarily needed for a given application in a class, like SSH, Bash, Fortran, compiling things, submitting jobs with Slurm, and all that other stuff, which, I mean, if you're going to do a PhD in computational material science, you need to know these things. But if you're just going to do exercises for a week in a class, you don't want to have to worry about all that. And so we have this nice graphical user interface. Here's an example from the Quantum Espresso tool, not the one we're going to focus on, but anyway, just to show you one of the other things that's in there. We're going to focus instead on the SIESTA code, mostly because it is faster, at least under some circumstances, for these kind of calculations. This is a code that uses numerically defined local orbitals. It's also an open source and widely used code in condensed matter physics and material science. Here's a reference to it. It's been around since quite a while, before 2022. And here's an example now of what we can do in that interface. Same kind of idea. We have these little drop-down menus, and we can fill in things, and then the nanoHUB tool is going to visualize structures and also plot things for us, like a density of states. Okay, so what are we actually going to have the students do? So the setup for this cure is, first, I gave them a guest lecture in which I introduced the concept of condensed matter physics. I told them about 2D materials and quantum dots. We went through the conceptual tools of isosurfaces and envelope functions, which I'll show you in a moment, that they had to engage with in the lab exercise. And I brought up the research question, which I just told you. And this is one of 7 lab exercises in the semester for which they had a 6-hour session to complete. The other ones were all some kind of more traditional experimental things, like looking at the optical spectroscopy of hydrogen or doing the Frank-Hertz experiment or something like that. And so what they did is, first they had a warm-up on square wells and envelope functions. I'll show you that in a moment. This is actually not with nanoHUB, but a different tool. Then they went to check out isosurfaces of the hydrogen atom. So this was to help understand the idea of looking at isosurfaces of wave functions with the familiar 1s, 2s, and 2p things. Then we went ahead to all look at the same 2D material heterojunction, molybdenum disulfide and, sorry, I think that's a typo, molybdenum diselenide and molybdenum ditelluride. And they did not relax the structure to make it quicker, and took a look at the potential of density and the wave functions. So this was to help make sure they could compare with others, and we could be sure whether there were any problems that we could resolve them. And then I gave everybody a different pair of materials out of this list here. So we've got molybdenum and tungsten, we've got oxygen, sulfur, selenium, and tellurium. So it gives actually quite a lot of possibilities here. And they would relax the coordinates, as of course the bond lengths and lattice constants are not the same for all these materials, and that's something that's relevant for this behavior. And then again, they'd look at potential density and wave functions. And I gave them a defined protocol of how to follow this so that we could hopefully have comparable data from all of the students. And then I had mentioned that one of the key aspects for a cure is to provide some way for students to have input into the project. So I asked them to also look for something else interesting in the calculation results that was not part of the defined protocol. So they could just dig into a lot of the other rich outputs that come from the SIESTA tool. So here's a couple things about the conceptual ideas that I presented to help them understand. So this is about isosurfaces, which is a key way that we try to visualize wave functions usually. And so I compared this to isobars on a weather map. I also showed them a contour map for hiking. And they're also familiar to some extent with equipotential lines that one talks about in discussing electricity and magnetism. So that was helpful. And of course, mathematically, this is a set of points where some function, such as the pressure or the potential, has a given value. And we even did a little practice thinking about a wave function for carbon monoxide here, and thinking about the relationship between these contour lines in a 2D cut and the isosurfaces that you get at different values of the iso value. So we can use that to figure out, basically, because there's this really big lobe here by the carbon atom, that means that we're going to have larger values of the wave function here. Okay, the other key concept that I needed to introduce was an envelope function. So, I mean, it's basically impossible to have something that is literally the particle-in-a-box model. What we get instead is something where the wave functions look like the particle-in-a-box model times an oscillating function. And so it's an envelope function, as shown here in a just kind of generic wave form. That's the thing that's going to look like the particle-in-a-box model. And so this is a concept we can see in various concepts for waves. It's the one behind FM and AM transmissions on the radio that we use. And then it's also a key idea actually for block functions, which is what I showed here. Yeah, so this is some kind of introduction for them with some examples. Then we went specifically to consider for the kind of system that we're thinking of how this can apply. So in a confined system, we're going to have an actual potential which may be flat in some vacuum region, and then it's going to be wiggly because of the atoms at the bottom. It's a sum of atomic potentials like this. And then we're going to get a wave function that looks wiggly like this also. That's kind of hard to interpret, but in many cases, we can think of sort of smoothing this out with the idea of an envelope function into having an effective potential that is square, and then an envelope function where neither of these have wiggles. And this is how we sort of make that construction of trying to identify what this envelope function is, thinking there's some atomic wave functions that we can basically divide out and then apply that in making this simplified model. This is also related to the idea of bringing in an effective mass for the electrons too. Which one could then use in trying to understand what the energy levels are for this. Here's an example that's actually from my thesis and using basically the SIESTA code for this. So I was studying molecular electronics, and what you can find is it's actually a pretty good model for having states trying to make their way through a molecule like this between gold leads, and it actually looks like one of these potential barrier scattering problems where you have a wave coming in, there's an exponential decay, and then a wave going out. And so on the left here, that's a calculation of the scattering state in the system. So you see there's a lot on the left-hand side, and then there's an exponential decay across the molecule, but with some wiggles that are related to the character of the particular orbital. And then something I actually did in this in work in my thesis was to divide this by an exponential fit to this, and you get something now that is no longer decaying across here, and it looks like the molecular orbital of the molecule that can be calculated on its own to help identify which orbital is responsible for this conduction. Okay, so now getting into some of the actual exercises that they did. So so this is something using the PHYS project, which is a nice project of little simulations for all kind of areas of physics, things that are much simpler than what we have in nanoHUB. And they have a quantum bound states exercise. And so you can see it has a potential like this. So we just have a series of square wells, and it will calculate the energies and the wave functions for you. And so I had them do this, and they could calculate something like this that has these oscillations from each individual square well. But then you can try to plot an envelope function over that, and this is the student's sketch on it, and then compare that to the wave function of an individual square well. And so you can see that this wave function on the left here is equal to the envelope function basically times this individual wave function from a particular square well here. And I asked them to look at several different states here. Most of them got that. What was a little bit more tricky, and I want to think for the future about how to explain this better, is what happens when we get something that changes sign. So the one here, this is actually built from the same little square well solution, but the envelope function actually now changes sign, like the n=2 solution from the particle-in-a-box. Many students got confused and thought that this actually comes from a different square well solution. Okay, so after they did that that warm-up, then they went to checking out the this common benchmark, MOS2 and MOTE2. And what they did here is they calculated a bunch of different wave functions. So these are 4 around the Fermi level, and these green things here are the way that this student sketched out the amplitude of the wave function. And you can see we actually have a series of states that look quite a bit like what you might expect from the particle-in-a-box model. So state number 71 in the valence band is localized in the MOS2 region, and there's not much in MOTE2. Number 72 is the reverse. 73 again is in the MOS2 region, and 74 is also in the MOS2 region. So you can see how we can identify the confinement in this way. Yeah, these are also some sketches that I had made from an earlier version on this too, where, so this is an example, okay, with a different pair where, so this is sort of the case. There is no confinement here, right? We don't really see any difference of what's happening in the two regions. Here's one where we actually have a node. So in the MOS2 region, we actually have a sign change between negative and positive. So blue is one sign and red is the other here. You know, we can have cases also like this where there's a sign change between the two different materials. So some examples of different things we can see there. Here's an example from one of the individual calculations that I had them doing. And this is actually WTE2 and WSE2. And in this case, the student actually did find a sign change, that it went from blue to red to blue here. So we have nodes in the middle there. This is actually correct for the envelope function, but evidently some more effort on the concept of node is needed, as the student had actually labeled this as known nodes. Okay, then we also had a look at actually the potential and the density. I think in retrospect, this maybe took a little bit away from the wave functions, but was also interesting to look at. So you could see in this WTE2, WSE2 system, this is an isosurface. So the surface is a little bit farther away from tellurium. And so if you think about this, what this means is this potential well for tellurium, if it's extending farther away from the atoms, that means that it's deeper than the one for selenium. So we have a deeper potential at tellurium. If we look at the density, we see also that the density is extending farther from tellurium, so that means that there's more density on the tellurium atoms. I had asked the students to think about electronegativity. I think this actually does not offer any simple explanation, unfortunately, in this case. But anyway, that's something one can look at. That's of course related to how many wave functions are confined in one region versus the other. And then finally, an example of when I asked students to look at some other aspects. Many of them took a look at the band structure, which is interesting. You know, so a mechanical engineering colleague once said to me something like, you know, you guys in physics like to look at these spaghetti things, right? I mean, this is of course a very extreme example of band structures looking like spaghetti because it's from this big supercell. So this is pretty complicated to analyze, and they had not learned about band structure in the class yet at all. But many of them noticed the fact that there is a band gap in here, which is certainly the most interesting thing to check out. I did not want to focus on this in the exercise because, as anybody who's familiar with DFT probably knows, you know, the band gap is one of the properties that we do not expect to get very accurately in DFT. On the other hand, it is still interesting for them to look into. Particularly, one can see, you know, these classic type 1, type 2, or type 3 things going on here. So, okay, it's hard to tell, you know, what's on one material versus the other in this plot, but you can see whether it's 1 or 2 where there still is a gap versus in some cases you actually get this type 3 case where the band offsets are so large between the two materials that you end up getting something metallic, in which case you would, in general, have a much less of this quantum confinement behavior. Okay, so you know, setting up this kind of activity is complicated, of course, and there's all kind of technical issues to work through, as well as the pedagogy. And so some of the things that I improved from 2022 to 2023, based on student feedback during the exercises, among other things, is I revised how the square well exercise worked. Actually chose a different benchmark calculation, which more clearly showed the confinement aspect, which helped students understand what we were really looking for. I did some improvement of the way that the XCrySDen tool works for SIESTA here for visualizing wave functions. We'll see a little bit better. And then also I found that having 4 unit cells wide in the structure made it much easier to see the confinement in many cases. So the calculations take a little bit longer, but the payoff in terms of clarity is quite a bit better. And some other things that I'm planning for the future are to try to explain better about wave functions and nodes, improving the way the band structure is plotted, trying to make some improvements about how these different functions are plotted with respect to the atomic structure, which is still a little bit clunky here. Some students were confused about these open-ended parts where I asked them to look at things in general, which is sort of partly on purpose, but partly not. I would explain to them what the purpose of doing this is more. And of course, this can be expanded to other different kinds of pairs of 2D materials. Here's an example more of the feedback part here. So I surveyed the students and they said in general that they found that this lab was actually about the same in difficulty as the other ones, which is fine, that it either increased or left similar their interest in physics research. They found it much more interesting than the other labs, which was good, and that it either increased or left similar their interest in physics in general. I asked them what part of the lab you find most interesting, and one of them said, the fact that I had no real idea of what the results would be, which is, of course, the nature of research. And one of them said that they liked programming and creating models on the computer, as well as that they thought the visualization of the materials was cool. And so that's one of the things we'll look more at in a moment. And I've always thought this too, so I'm glad that they agreed with that. So some conclusions is that by using these GUIs in nanoHUB, we can focus on the quantum physics that we want to teach and not necessarily on the computational methods. Although, of course, there are other ways to use the tools if that is what you want to teach. That even for sophomore students, that they could do real, serious condensed matter theory calculations here. They were enthusiastic about this, and I encourage you to think about how to use nanoHUB and perhaps the idea of a CURE in your own courses. I'd like to acknowledge, of course, the students in this class, both years, for being participants as kind of guinea pigs in this activity. One of my students and postdocs helped to facilitate the lab activity. This is actually not the course I'm teaching, so the course instructors, I have a typo here, oops, this should be Dustin Kleckner, and the TAs for the class helped collaborate with me to make this happen. Of course, I've gotten a lot of support from the nanoHUB team, especially Stephen Clark in managing to get all of this stuff working. And my participation on this was funded by an NSF Career Award. So that helped make this possible. So yeah, I'll stop for a couple of questions at this point, and then we'll go into looking at some demos of how we actually do some of this stuff in there. So what have we got for some questions?
Yeah, so we have a question. Do students use other software to set up the initial structures, or is this part of the nanoHUB GUI?
That's part of the nanoHUB. Yeah, we'll see that. We'll see that in a moment. I'll show you how we get one of those set up.
All right. And then someone asked, is there any possibility to calculate the band structure involving more unideal factors like interfacial charges or oxide layer?
I mean, that's a great question about what happens in reality. But I think the short answer is no. I mean, I think in order to do that, you would need to actually have a surface below it or something, which of course one can do in here. It greatly increases the complexity of what you're trying to do, but it is possible. We do actually have the ability to apply an electric field, which could get in a little bit of what you're thinking of.
All right, thanks. Another question, in DFT, how can the selection of the cutoff radius and basis set affect the accuracy of calculating a specific property?
I mean, it affects everything. In principle, yeah. So, I mean, the usual way within Siesta, why don't we go to, I'll start pulling up that tool to show where this comes in. Yeah, in principle, it affects everything. So every kind of a different calculation we can do in DFT has different sort of parameters that have to be converged, and the size of the basis set is the main one that we would use within Siesta, but there is also a cutoff radius for the orbitals, as you're mentioning there, and yeah, all kind of things can be different if you use something that's too small. Okay, so for the kind of second part here, I'm going to show you explicitly how we do some things in this tool, including some other aspects that I found useful in class that were not necessarily involved in this one, but I wanted to share with you. So to start with, here's the tool, and I brought up the page for supporting documents, so you can see there's all kind of things here. Some other kind of webinars and classes, including some that I and my former student, Dr. Guerrero, presented in 2022. And then down at the bottom, these last three are ones that relate to this this one today. So these are my slides. This is actually the lab manual for the exercise, which I'm going to start looking at a few things in. And then I also put up that you might find helpful, some notes on visualization of structures with XCrySDen, which is not specific just to nanoHUB here, but can be helpful. Okay, so we're going to launch the tool, and then I'll show you about what we're doing with the basis set in there. And we're going to start by setting up this calculation of the benchmark, which I had asked students to do.
While that's loading, maybe I can ask another question that came in. Were there any challenges with getting students used to the open-ended nature of the cures instead of their cookbook labs?
Yeah, I think some students felt like, can't you just tell me exactly what I'm supposed to do here? I mean, one of the comments I got was that they felt like the lab manual just kind of trailed off in not having the same level of detail toward the end. And I think that's actually exactly the point where I was trying to have them fill things in and find something else. And I mean, if I told them exactly what to look for, then it would no longer be the part of trying to look for something else on your own. But yeah, this is always one of the issues with some kind of more interesting or innovative things one can do in pedagogy, that often it asks more of the students. That's the idea. And if you don't ask more, then it probably doesn't have a beneficial effect. But students either they have to get used to this idea of what you're looking for, or in some cases they would rather not do more. So you have to carefully motivate what you're doing to make sure that they understand what the purpose is and get them on board, which does seem to have worked pretty well here. All right, so back to the tool here. So I've pulled up the Siesta tool. You can see out of this different menu of things we have, and so I'm going to follow along what I've got in the lab manual on the benchmark calculation. And so we're going to start with selecting a exchange correlation functional. I'm going to set GGA. We've got a total energy. The other choice would be geometry optimization, which is going to take a lot longer here. I had them do it, but it's even beyond what we can do for this session. We're going to set double zeta with polarization. So this is a question of where the convergence of the basis comes in. So we have three options here. DZP is often enough, although one could certainly go beyond that. And then we've got some things about visualization. One thing I think which is nice that we have here is actually the test calculation. So you can check that you've set up the structure properly by doing that. It just kind of turns off all of the actual DFT calculation and goes straight to visualization. What we're gonna do is we're gonna tell it that we want to look at the potential. Actually, yeah, let's forget the potential. We'll just look at the wave functions here. And we tell it which wave functions we want to look at. So I'll go to wave functions 72 and 73. So that's going to be the valence band maximum and conduction band minimum. You can count up the number of electrons you've got in order to figure out what these numbers are, or you can just run the calculation once and determine what it is and come back again. Okay, so then there was the question about how do we actually set up the structure and did we need to use some other software? So that's one of the nice things about this GUI. So, I mean, you can enter anything you want, but we have a lot of examples in here. So I'm going to go to sheet/slab, which is appropriate for a 2D material. I'm actually going to set both of these to 1 to make it a little bit faster. Out of plane lattice constant, so that's the sets the vacuum space that we have. And then here's the key point. Among a bunch of different examples, including some diamond and silicon surfaces, we're going to choose molybdenum disulfide supercell 8x1. And so now here, this is a pure MOS2 structure all set up nicely for us. And all we need to do now to turn this into MOS2/MOTE2 is this is all ordered so 8x1, there's 8 unit cells here. We're going to leave the first 4 as MOS2, and then we're going to make the last 4 be MOTE2. So I just need to go in here and just do a little typing. So that's 2 cells that are changed, 3 cells, and 4 cells. And, that's all that I had the students do, right? In some cases, they did tungsten, so you change MO to W. You might change the first half in some cases, but that's all we really need to do to set up the structure. And just double checking over here. So, okay, so that's all we need. I'll mention just another fun thing. You can actually do run in parallel as well for big calculations here. This usually works pretty well. It sometimes makes it the wait time is longer for it to get started. So we actually don't need it in this case. The runtime should be fine without that. So I'm just going to hit simulate. So that's going. This might take as much as 5 minutes. So I'll fire up another thing to show you in the meantime. Right, this is just kind of showing us all of the output so we can see something's happening. We're going to go to the first thing that I had them do in nanoHUB, which is looking at the wavefunctions of the hydrogen atom, which is pretty quick. Here we go. Okay, so we're going to do this in SIESTA again. This one is very quick for just a single atom, which is nice. So we're going to leave it at, we may as well use double zeta, and we want wave functions, and we're going to ask for 1 to 5. This is actually going to give us 1s, 2s, and 3 2p orbitals. We can go to molecule, and just going to type in some things here. You see it's a little prompt about what we need. So that's going to give us the hydrogen atom. And due to some slightly annoying things about the GUI that I don't fully understand, I need to try to make this a little bit bigger to get everything to work. And here we go, it's computing. All right, and so now we have a little XCrySDen window. So I want to just mention, so this is a standalone visualization piece of software that a lot of people use on its own. And we have it kind of baked into SIESTA and Quantum Espresso tools so that we can look at data. We also have it separately in nanoHUB. Okay, it looks based on the time. I'm not sure I'll get to looking at that, but you can do some other interesting things in there in visualizing structures, Brillouin zones, Fermi surfaces, Wigner site cells, and stuff like that. And you can even just upload your own files into that to visualize it. Okay, so what have we got here? So this is a hydrogen atom. This doesn't look very inspiring, but we can go to data grid, and you see it's got the charge density that's loaded up. Okay, that also is pretty boring. But what we can do is actually say close and then open up a new file. So I will admit I was kind of proud of myself when I realized that this was possible. So I think this is sort of not quite the it's not a thing you might imagine that you were able to do here. We're actually looking around on the in the directories on the computer where this thing is running, but it's put all of the files in the same directory. And so these are options of what we can look at. This is the charge density difference from the atoms. That's the charge density. And then these wave functions are, the first one is 1s, that's 2s, and then 3 2p orbitals. Let's just stick to one of the 2p's, which is the most interesting. And so to visualize this, I'll go to the data grid and just say OK here. Now we have some settings about the isosurface. So typically 10% of these maxima is a good value. I'll say render plus or minus. So it's going to show us both positive and negative parts. And then we say submit. Okay, we have to go back to the original panel. Okay, it just looks blue. But if we zoom out, you can do that with the mouse scrolling, right? Suddenly now, hey, that looks like a p orbital. I can turn on the axes here, and we can have a look, right? That looks just like what our chemistry textbooks will tell us. An interesting thing to note, which is good for thinking about degeneracy and stuff like that in quantum mechanics. So if you ask, given our coordinate axes, is this px, py, or pz? I mean, it's kind of none of the above. It's actually pointing in a different angle, and that's because these orbitals are all equivalent, actually, and so it's a little bit random or arbitrary which one we actually get in the calculation. And one of the nice things we can do with isosurfaces, trying to understand how this works, is try to see what happens when I pick a larger value. So I'll set this so this isosurface is just about the size of the screen, and then I'm going to go here and I'm going to make it bigger. So let's try 0.2 instead of 0.6. So it's a larger ISO value. Let's see what happens. It was just the size of my screen, and look, it got smaller, right? And so that's the general thing we'll see. A larger value of the isosurface is going to go closer and closer in towards the atoms, and smaller values are going to go farther out away from the atoms. Okay, and finally, let's come back to... Okay, all right, this calculation is actually almost done in the on our 2D heterojunction. So okay, let's just have a look at a different wave function here for a moment. Let's try wave function 2. So that is that's a 2s orbital. Again, I'm trying about 10%. And oh, okay, all right. Apparently, I'm mistaken. That's not 2s. The ordering is not quite what I thought. At any rate, that's the point of the visualization. So we see what we've got. So this is just a different 2p orbital, so oriented in a different direction. That's come up here. Cool. Okay, the calculation is done here now for the 2D. Oh, sorry. Yeah, okay. Anyway, it is done for the 2D material. So let's try a couple things here. Okay, so first I'm going to say close and then bring up one of the wave functions. So I'm going to try wave function 72. That is the valence band maximum. And I'm going to go to data grid again. I'm going to pick out, about 10% of the maximum here. You see these numbers are not the same. And now this is a slightly annoying thing that I discussed in the manual. There's supposed to be a submit button here. Sometimes it doesn't show up if we didn't make the screen big, so I have to actually close this, go back to data grid, and now it's here. Okay, submit. And there we go. So now this is the kind of wave function that the students are mainly looking at. So we can see, right, it is localized in one side and there's very little on the other side. And we can also go to atomic symbols. Annoyingly, the default colors are the same for some of these atoms. But now with the labels, we can see, right, this wave function is in the MOS2 region, and there's not much in the MOTE2 region. And so that's the key thing that the students were trying to see here. Okay, well, looking at the time, I think, okay, those are the key the key features that I wanted to show you. So why don't we go to some questions now?
Okay, great. So one question that we've had a few people ask is about the benefit in using Siesta over quantum espresso.
I think typically it's probably a bit faster for these calculations, maybe a bit harder to converge to a given level of accuracy, but this certainly could be done with quantum espresso as well. Yeah. So I mean, yeah, this is a somewhat arbitrary choice.
All right. Someone said, I see band shifting issue in Siesta. How can we minimize this issue? And can we use Siesta to study magnetic properties?
Yeah, so by band shifting issues, I mean maybe what is meant is about the question of what band is at zero or where the vacuum level is. I'm actually not 100% sure. I mean, I think I think it's just a question of whether it is whether you understand correctly what's being shown in the band structure, namely that zero here is the Fermi energy, not necessarily where the vacuum is. Can we study magnetic systems? Yes, absolutely. So if we go back to the input panel here, right, there's a spin polarized thing here. You know, maybe I'll do it in the other pane just so it doesn't possibly lose my calculations. But for example, if we go into the solid and we look at an example, we've got iron, BCC, and FCC. So, you know, we can set it to spin polarized. That's actually the default here. So we can calculate ferromagnetic iron, and you can certainly do some other kind of magnetic systems if you like in there.
All right. Someone asked, is it possible to show students closed form expressions for the wave functions? Is it built in Siesta or would Wannerizing be needed?
I mean, there isn't a closed form expression. Siesta uses a numerically defined grid. So, no, you know, unlike say, I mean, if you use, for example, the games code that we also have wrapped in this tool, then it uses Gaussian type orbitals, and then you can write down, of course, what the form is. But with Siesta, I think it's not particularly illuminating to consider what exact form of those things is. Yeah, I mean, you could try to linearize this for this particular exercise. I don't think there's a lot of value, but that's one way you could try to generate the band structure or other kind of properties.
All right. And someone asked, is it possible to calculate the capture cross-section or capture rate coefficient like we do in VASP?
I mean, I'm guessing that that's about defects, about capture of electrons and holes. If so, I mean, yes, in general in Siesta, but that's a kind of advanced. Okay, yeah, for defect, I mean, there is a vast space of different things one could do with DFT. We only have a small fraction of that so far within these tools. But I mean, since you asked about that, I'm actually working on a couple of grant proposals right now, which would involve doing some enhancement of the ability to do some calculations about defects within these tools. So maybe coming soon.
All right, great. And I see in the chat someone said, thank you for sharing. I will be adopting these tools for use in the fall. That's great to hear. A couple of people are asking about running the tool in system configuration. So in nanoHUB, all the tools just run in your browser. So as long as you have an internet connection and a browser, you're able to run these tools, and it's also free to run in nanoHUB.
Did we get to this one? Can you give a quick explanation about DM tolerance to improve the relaxation?
I would say maybe no. This is not This is not a parameter that we actually allow to be manipulated within here. So I guess we have a Siesta expert asking this question. I mean, if I remember correctly, DM tolerance is I mean, DM is for density matrix, so it's about the degree of convergence of the SCF. And I mean, if your SCF is not converged enough, then clearly that will cause trouble in the relaxation. Beyond that, I'm not sure I have much insight to offer. Under most cases, a default for that is okay. So don't mess with it here.
All right, and someone's asking if there are any tutorials for DFT. So we do have that DFT users group in nanoHUB. I will link the group once again, and we have our webinars related to the topic in that group.
Yep.
And I'm also...
Yeah, I was just going to say, there. If you look at, there's actually a bunch of, course resources and things that go along with this tool here. So, for example, right, you can see there's this thing here that says, introduction to DFT, Quantities method, etc. Also here, this is the whole overview of computational nanoscience. That's the original course that this was developed for, which has lecture slides about, all of the different kind of computational methods in here, which has a lot about DFT.
So it looks like we're just out of time now. I think we answered most of the questions that we had coming in. So once again, thank you, Dr. Strubbe, for the great presentation, for letting us know how you use nanoHUB in your classes. We really appreciate you being here, and I hope everyone on the call has a great rest of the day.
Thanks everybody for joining. It was fun to do this, and I hope that you can find these tools useful in your work.